Check this out, and that's completely true. That image has 281,912 black pixels precisely. If you add up every pixel and all the characters and all the digits of 281,912, there are exactly that many pixels. And if you're wondering, how did we do that? Well, not only am I going to show you how we did it, I'm going to show you how you can do it. I was originally inspired by this post on Reddit in the MathPix subreddit, yet again, origin place of the trumpet. And that image does have 76,018 black pixels. Now, this is a little more simple, and there's no other text. It's just a number which needs that number of pixels to render its digits, which got me thinking, what is the smallest number for which that is possible? A question, like most things in life, we can solve with a spreadsheet. I set up a spreadsheet so I can just do pixels by putting a 1 in a cell, boom, pixel. Now, here's the first philosophical question. Is that a 1? It's kind of a 1, but the thing is it's as horizontal as it is vertical. So it's an underscore as much as it is a 1. So 3 doesn't work. Let's have a go. 4 pixels. Does that count? This is where I think things start to work. 1, 2, 3, 4, 5, 6, 7. That's a 7. In fact, 7 pixels are enough to start getting fancy. 5, 6, 7. That's a 7. So the point is, this does work, and it starts working at 7, and seems to work pretty consistently from 9 onwards. But we're not including any text yet. To add some text, my search for a tiny font led me to this Reddit post, which I think will work nicely. And I think the shortest possible description is just the word pixels. So I've taken the characters for pixels, I've put them into the spreadsheet. Now because each of these cells turns black when I put a 1 in it, it means I can do the sum of, let's just grab all of this. If I add all of that, there we go, currently 35 pixels. So we need to add, well, it can't be a 1-digit number because we've already got 35, a 2-digit number which will add as many pixels as the new sum when you add on 35. 45 is 46 pixels, but I could turn this, I remember the 6, let's bring the 6 back up. Was that the 6 there? Oh no, that's 48. Gone too high. Wait, what's the 7? So the 7, delete all this. Oh no, wait, that's 1, that's 1, that's 1. 47 pixels. Has 47 pixels. Having found the smallest, I obviously now wanted to find more of these. Nay, all of these within reasonable constraints. And while a spreadsheet would be fun, and my terrible Python code probably adequate, I wanted something a bit more robust that everyone could try. And thankfully my friend Christian Lawson Perfect put this together for me.
Here is Christian's fantastic website. I'm actually going to change the default text to just be a look. And then the $sign is like the break symbol. That's the number that's going to appear. And instead of opaque, I'm going to switch it to black. And we can start at font size 10. And let's go all the way up to 30. Why not? Here we go. And look at that. Look at it go. So there was one solution for font size 10, but look how small it is. Or I must admit, I'm now doing all of this at HD. In this specific typeface in Lee Gothic, at that size, for this wording, that little image there has exactly 578 black pixels. But you can see the small ones don't render very well, and the big ones are much better. Look at that.
If you're wondering how Christian's website, well, the code behind it, is able to find these solutions, it's doing pretty much exactly what I did to find the 47 pixels solution. Puts in one number, counts the pixels, changes it to that new total, and repeats and does that iterative process over and over again until it hopefully finds a solution. Now, if this iterative process of going from one state to another sounds familiar, it's because it happens all the time in mathematics. So of course mathematicians have a host of tools to deal with it. They will plot the entire thing as one massive network, which for some reason mathematicians call a graph, and that can give us an overall snapshot at once of how everything links together. And so of course, Christian added that as a feature to the website. In the graph section on Christian's website, we can pick a 22 size font, show the graph, and look at that. Now, you can see there are two yellow nodes. They're the ones that actually work. That is 910, and there's also 916. All the other ones are possible starting values. So if you were to put any of these numbers in as your first guess, this shows you the path where the next guesses in the iterative process would happen, in this case eventually ending up on 916 or other ones on 910. So we saw the case for font size 22 and there's the two solutions we could see, but what about something like 24 where there were no solutions? Well, if you look at that graph, there are no yellow ones because none of them iterate back into themselves. Every single point follows a path and then ends up in a loop. So you can see in this case, your iterative process will forever bounce between these three values, and that's where the code gives up.
Now, obviously, we will make Christian's website available, so you can check that out. Hey, speaking of websites, this video is sponsored by a website, surfshark.com/standupmaths. Oh, they've gone. Anyway, it's me, Business Matt. We're sponsored by a VPN. You know what a VPN is?
A virtual private network encrypts all of your data locally, so no device, service, or person between you and the internet knows what data you're actually sending. And while a common feature is pointing out that you can decrypt that data on a server in a different country and pretend to be connecting from somewhere else, there are other uses.
Of course, here at Stand Up Maths Limited Enterprises, we benefit from surfshark.com/standupmaths. So regular Matt, when did you last use a VPN? Well, funny you should mention it. When we were planning all of this, I had a video call with Christian, but the hotel I was in Hong Kong, wouldn't let me use that service. I turned on a VPN, it had no idea what all those ones and zeros were, and I could make the call. Now yeah, that's enough backstory, okay? Right, the point is, you can go to surfshark.com/standupmaths or just use the code standupmaths for 4 extra months. And don't forget, it's a 30-day money-back guarantee. Give it a go. Thanks to Surfshark for sponsoring this video. Thank goodness that is over. So, as I was saying before, we will make Christian's website available. There'll be a link in the description below. I'm also going to link to another video because when I dug into the original Reddit post about the 76,018 pixel image, it was inspired by a video looking at making referential charts. This video here, which also came out 9 months ago, and in this, Carrie KH, oh look, I haven't subscribed. I'm going to subscribe and like the video, like everyone should do when they're watching a video they like. Looks at recursive sentences, but these sorts of referential charts actually track back at least to this XKCD comic from 2010, and this is the same idea. Each of the panels are self-referential panels that refer to all the other panels. Absolutely amazing. I remember when this came out, and of course nerds analyzed it. So John here used the Mathematica programming language to recreate not only Randall's original XKCD comic, but then because they had it all coded up, they could change it to be color. I mean, look at this. Now each of the panels with 4 colors are referring to each of the other 3 panels. Very clever, John. Now this code's lovely, but if you're wondering how was the original XKCD comic done, well, a couple of years after that, my friend Laura Talman interviewed my friend Randall Munroe. You know what? You can hang out with your friends, but it's so much easier if they just interview each other and then write it up for you to read later. And in this interview, which I'll link to below, Laura did reference that comic and asked, having mentioned the Mathematica code written by John,
"Is that how you found it, or did you find it another way?"
And Randall replied,
"I found it another way. I didn't actually write any code for this."
Turns out he did it all, quote, by hand in Photoshop and just iterated in. So you can see here, he says,
I think there were about 10 or 12 iterations.
So there you are. The original one wasn't even using code. And I have to agree with Randall when he says,
I always go for the lazy solution that doesn't require a lot of new stuff.
Hence my love of terrible Python code.
I'll link to this interview, the other pages I showed, and of course the Carrie KH video in the description below.
There's one thing we have to acknowledge and deal with now, and that's that the images coming out of Christian's fantastic website, no shade on him, look a bit janky. They look weirdly low resolution. When they're not, they're exactly the number of pixels they claim to be. But if you look at something at that scale on a normal laptop, it looks different. And that's because we needed pixels that were either on or off. They were either like totally opaque or totally transparent, which is why
it technically says number of opaque pixels, and it seems pixels don't actually behave like that, particularly when you're rendering a font. So to get to the bottom of this, I thought I'd better speak to an expert. My friend Linus Bowman has an amazing channel about design and typography, and I asked him how a font's actually defined. So how does a computer take those vector curves and turn them into pixels?
Good question.
Because naively, I would think it looks at each pixel and checks if there's more of it inside or outside the curve, and then it's white or black accordingly. But I got a sneaking suspicion it's not that easy.
No, it's never quite that simple. Fundamentally, yes, it's kind of checking, is there a filled shape here, or is it negative space? But then as soon as you start drawing curves, or even if you have a straight line, if you think about a sans serif eye, the most basic shape, a long rectangle, even displaying that, if you have them not perfectly aligned to the pixels on your screen, how do you decide what fraction of the edge of this line should be rendered here versus on the other side of the line? And so there's been lots of different technological solutions to that over time.
So it turns out we're looking at fractions of a pixel, sub-pixel rendering. And I asked Linus to explain that to me as well.
So, I mean, sub-pixel rendering is a really interesting solution to this problem. And I think the mainstream kind of solution was a proprietary system called ClearType by Microsoft. It works on the principle of that a pixel is not really a pixel. It's actually kind of 3 bars of color. It's RGB, red, green, blue. And they are uniformly in the same order. So you kind of always have the red on the left, the green in the middle, and the blue on the right. Unless there may be exceptions on certain brands of monitor. But then, if you know this information, you can kind of feather the edge of a line more to the left by using turning on the red. No, left. Okay, I'm going to get my orientation mixed up. But you can shade one side of a line a little bit more by using red versus blue, etc. That's the fundamental idea. When the default font changed to Calibri in Microsoft Office from Times New Roman, I think around 2007. And that was because LCD monitors were kind of supplanting CRT displays in the market. It was a lot of the kind of basic anti-aliasing technology that developed previously worked better on CRT, or aliasing was just less noticeable on CRT displays, and it was much more jarring to see it on LCDs, especially those early LCDs. So that was something then that they put a lot of development money into, making these very well-optimized fonts using that technology, and using a really strong process, a very technical process called hinting, which actually doesn't leave it up entirely to the program to interpret which pixels to turn on and off and which subpixels to turn on and off.
We can actually see what's happening at the pixel level by using a microscope. So if I put this on actually the top of the original Reddit post, over here, if I position it right, you can see the text. Let me see if I can get it up the right way. That's probably it there. Okay, here we go. So that's not the number in the image, that is the number in the title of this Reddit post. And if I zoom right down to the pixel level, so you can see each pixel in the screen on my laptop is just vertical stripes of red, green, blue, red, green, blue. And where we hit the edge, the pixels don't all like turn off abruptly. So they don't come on and off in batches of 3, even though technically we're looking at pure black on pure white. It decides where in the red, green, blue alternating pattern to turn on and off. So it's not operating a whole pixel at once, it's operating fractions of a pixel. It's using sub-pixel rendering to make the edges of these characters look smoother than they would otherwise. And that's why the images coming out of Christian's website look a bit janky, because they're rounded to the nearest whole pixel. Now, while you could consider subpixels ruining everything this video stands for by not rounding to the nearest whole pixel, I saw an opportunity. I was like, wait, I can now make the smallest self-referential number ever. And what you can see here, I had to put an arrow on it because it's really hard to spot otherwise. In Photoshop, I went in and I turned 3 pixels, one on top of the other, pure green. So all we should have is the green line turned on, which means we've now got a 1 made of 3/3 of a pixel stacked on top of each other. It's a proper 1 using a total of 1 pixel. It's just 3/3. Although finding it is a little tricky. So there's the arrow. There it is. What? There's some red. Okay, so there's some kind of color representation thing going on where for some reason the reds are turned on slightly. They shouldn't be. Ignore those. That's technically 1 distributed pixel across 3 subpixels. That is 1 pixel representing a 1. Smallest referential number in the world. So in conclusion, what now? I mean, given, as far as we know, the story started with an XKCD comic in 2010, went via a Carrie KH video like last year, and now, via a Reddit post, here I am. And up until now, what we've been doing is always adjusting the number. So you start with everything you want around it, and then you find the fixed point where the number stops changing. What if we fix the number and change everything else? Now that's a much harder search to do, but we've done it for everyone's birthday. So happy birthday. I mean, for like 1/3% of you, that was correct. I've got a birthday present for everyone here, and you can use it to give a birthday present to anyone else you know.
Of course, Christian has put it on the website as well. So over here, you can pick your birthday, which for me is right over here. And there it is. There's my message. You can change this to whatever date you want, and it does the reverse lookup by tweaking the words and, of course, your magic birthday word to get the exact number of pixels. Oh, it's so good.
If you want to see some more of these, just hypothetically, because I'm going to be at the Edinburgh Festival Fringe soon, from this date until this date, we can use those as examples. And then I'm on tour for all of these dates. And while that's happening, I mean, link in the description below if you want to come and see me. Please come and see me. It's very embarrassing if there's no audience. Huge thanks to everyone who made the video possible. Of course, Christian Lawson Perfect did all the coding to make the website work for us. Link below, you can check it out. And Linus Bowman, fantastic channel. If you like design and typography, highly recommend you check that out. After you've booked tickets to see me. The London one, that's like 1,200 seats. We're in the same theatre that the musical Matilda is normally on, but we get to sneak in on a Monday night. Please come along. I have 1.2 kilo humans there to watch.